In this video, we're going to learn another application of integrals. We're going to use integration to find the length of a curve. And you might be thinking, well, you already know how to find the distance, a straight line length, using the distance formula. But yes, we do know how to do that, but the distance formula works for a straight line distance. And what if we have a not so straight line and we need to find how long it is? So let's just say we have some unusually shaped curve. I don't know, something like that. This is my curve C. And let's say that we want to find how long it is between these 2 points, A and B. Well, one thing that we can do is actually use that distance formula that we know and use it to help us figure out this arc length. So we need to divide this A to B interval into lots of little subintervals. I'm just going to do an example. Here I'm dividing this up into a bunch of little pieces. And then on each piece, we can approximate the length of that piece using a straight line. So I'm going to just use green here to draw straight lines between all of these points. And you can see that's pretty close to our curve. It's not perfect, but that's the idea of what we're going to do. We can find all those straight line distances using the distance formula. And then if we just chop this up into smaller and smaller little subintervals, so we're taking shorter and shorter straight line distances, add all of those distances up, take a limit, and what do you know? We're going to end up with an integral to give us the length of this line. So let's actually set up all of the theory. So let's suppose our curve C is defined by some y equals f of x, where f is continuous. And we're going to look between A and B. Then we can find a polygonal approximation for our curve C. And we find that polygonal approximation, and what that means is just using straight lines to approximate our curve. We can find this approximation by dividing our interval, AB, into n subintervals. With endpoints x0 through xn, and equal width delta x. So right now, this procedure that we're doing here should feel pretty familiar. Basically, everything we've done so far in Calc 2 is we've taken an interval, chopped it into n pieces of equal width, do something with those pieces, add them up, and take a limit so that we can have an integral. And that's exactly what we're going to do here as well. So even though it's going to be theory heavy at the beginning of this video again, it's the same type of theory we've been doing so far. So hopefully it's starting to feel a little more familiar. So if yi is defined to be f of xi, our function evaluated at an endpoint, then the point pi, which is xi, yi, lies on our C, and the polygon with vertices P0, P1 through Pn is an approximation of C. So we're approximating our curve using all these straight line segments, connecting all of these points pi. So since this polygonal approximation is approximating our curve, then the length L of our curve C is approximately the length of this polygon. So of all of those straight lines added up together. The approximation gets better as n increases. So the more subintervals we use, which makes the more straight line pieces, the better this approximation is. And as you can imagine, when we take a limit as the n goes to infinity, we'll get the actual length of this curve C. So we are going to actually define the length L of our curve C is equal to the limit as n approaches infinity of the sum from I equals 1 to n of the distance between pi minus 1 and pi. So that's the length of each of the straight line segments. So if our function f has a continuous derivative, that means it's a smooth function. That's what it's called. They're just very nice, well-behaved functions. We're not going to go too deep into that theory right now. Then we can define an integral formula for this L. To do that, we're going to need that distance formula that we learned way back sometime in an algebra class. So let's let delta yi equal yi minus yi minus 1, the change in our y coordinates. Then the distance pi minus 1 to pi is equal to, using our distance formula from algebra, the square root of the change in my x's squared plus the change in my y's squared. And if I rewrite this a little bit, change in x's is delta x. And then we defined yi minus yi minus 1 to be delta y. So, sorry, delta y I. So I have that this distance is the square root of delta x squared plus delta yi squared. Now, there is a number which I'm going to call xi star between xi minus 1 and xi, such that f of xi minus f of xi minus 1 is equal to the derivative of my function at fxi star times xi minus 1. Now, at this point, if I were teaching you face-to-face, I would ask you, why is this true? Is there a theorem that we know that says this statement? And hopefully somebody out there is saying, yes, this is the mean value theorem from Calc 1. Hopefully you remember the mean value theorem. If you don't, you might want to go back in Calc 1 videos and watch one on the mean value theorem. I'll put a link in the description just so that you can review it if you'd like. But this statement is true by that theorem. Using this theorem, my delta yi, which is equal to my yi minus yi minus 1, which is equal to f of xi minus f of xi minus 1. My delta yi is going to be equal to f prime of xi star times xi minus 1, using that mean value theorem. Just notice that this left side of the mean value theorem is equal to my delta yi. So using that mean value theorem, that distance between pi minus 1 and pi, which we already said was the square root of delta x squared plus delta yi squared, using that mean value theorem, I can replace delta yi squared by f prime of xi star times delta x squared. And this is equal to a square root of 1 plus f prime of xi star squared times the square root of delta x squared. So all I did there is I kind of factored out this delta x squared, and then I wrote it as a separate square root multiplied there. We can simplify that because the square root of the delta x squared is just delta x. So what we get when I simplify is that this is equal to the square root of 1 plus the derivative of my function at that xi star squared times, delta x. So what we have now is that the length of our curve is equal to the limit as n goes to infinity of our sum, I equals 1 to n, of the distance between pi minus 1 and pi. So that's all of the little polygonal distances added up. Using what we just found, this distance is equal to that guy right there. I get a limit as n goes to infinity of the sum from 1 to n of the square root of 1 plus the derivative of my function at xi star squared times the delta x. And now when I actually take this limit, the limit of that sum, we end up getting an integral. So when I actually take the limit as n goes to infinity, I get this formula for the length of the curve. The integral from a to b of the square root of 1 plus the derivative of my function squared with respect to x. All right, so those of you that don't like the theory, time to wake up because it's example time. This is the formula that we need to calculate the length of any planar curve, also called finding the arc length. That's the formula that we're going to be using for the rest of this video. We just have a few examples of calculating some arc length. Let's start with this example here. Find the length of the arc of the semi-cubical parabola y squared equals x to the third between the points 1, 1 and 4, 8. Now, don't be too concerned by the name of the semi-cubical parabola. All you need to know is the curve looks something like this, but we only care about it between the points 1, 1 and 4, 8. So we're trying to find the length of that curve between those 2 points. And so we're going to be using that arc length formula. Now, for the part of the curve that we're actually concerned about, we do have that y squared equals x to the third, and y would then be equal to the square root of x to the third, which is the same thing as x to the 3/2 power. Now notice when I solved for my y, I took a square root, but I only wrote down the positive root, not plus or minus, and that's because the part that I care about for this problem is above the x-axis, so I only need the positive y values, so I only have the positive root written down there. So this is the equation that we need for a function in between those 2 points. Now, the arc length formula involves the derivative of our function. So remember, the length is equal to the integral from a to b of the square root of 1 plus the derivative of our function squared with respect to x. So my f of x in this problem is going to be x to the 3/2. And so I need to find the derivative of that to plug it into this arc length formula. That's where we get to start. My f of x is equal to x to the 3/2. So the derivative of my function, using the power rule, is 3/2 x to the 1/2. And I need that guy squared inside of my integral formula. My length is equal to the integral from 1 to 4. I got those values because they were the x coordinates of the points I was concerned about. The square root of 1 plus the derivative of my function squared with respect to x. So if I calculate this integral here, I'll get the length of that curve. Now, how do we integrate this? Well, the very first thing that I would do is simplify this guy squared. 3/2 x to the 1/2 squared is 3/2 squared times x to the 1/2 squared. So go ahead and square that piece to see what we get. We get an integral from 1 to 4 of a square root of 1 plus 9 over 4, and then x to the 1/2 squared is x to the 1/2 times 2, which is just x. So I get a square root of 1 plus 9/4 x with respect to x. That is what I need to solve. Now, how do I do this integral? Well, I have a bunch of stuff underneath the square root. I can do an integral of a variable under a square root, but that's way too complicated. We need to use substitution on this. So I'm going to let u equal everything underneath the square root, and that means du is the derivative of that, 9/4 dx. And if I solve this for dx, I get dx is equal to 4/9 du. And now I'm going to change my bounds of integration because that's the way I like to do my substitution problems. If you don't like changing your bounds, remember that you can always integrate, plug your u back in, and then plug in your original bounds, and you'll get the same answer. But I'm going to change my bounds. When x is equal to 1, that means my u is equal to 1 plus 9/4 times 1. Well, that would be 1 plus 9/4, that's 13/4. And when my x is equal to 4, that means my u is equal to 1 plus 9/4 times 4. So that's 1 plus 9, which is 10. If I rewrite my integral using the substitution, we get that the arc length is the integral from my new bounds of 13/4 to 10 of my square root of u, and then my dx is 4/9 du. So now I just have to solve this integral. I'm going to start by pulling the 4/9 out in the front. And I'm going to rewrite my square root of u as u to the 1/2. And now I can use my power rule. I have 4/9. Antiderivative of u to the 1/2. You add 1 to the exponent, and then divide by that new exponent. Dividing by 3/2 is the same thing as multiplying by 2/3. Then I will have to plug in my 10 and my 13/4 and simplify. So looking at this number in the front here, 4/9 times 2/3 is 8/27. And so I get this is equal to 8/27 u to the 3/2, plug in our bounds. So I'm going to have 8/27 times 10 to the 3/2 minus 13/4 to the 3/2. And that is my solution. I personally would just leave my answer right here because I know it's not going to simplify to be very pretty. But we can simplify it a little bit if you like to. So, simplified version, 10 to the 3/2 is the same thing as 10 times the square root of 10. And similarly, 13/4 to the 3/2 is 13/4 times the square root of 13/4. Simplifying this a little bit, well, I can, let's see here. I'm going to go ahead and just make it a little bit prettier. I don't like having all these fractions here. So I'm going to distribute just the 8 through and leave the 1/27 on the outside. If I distribute that 8, I get 80 square root of 10. Minus 26 square root of 13/4. So that's still a little bit ugly. I can simplify that square root of 13/4 just a little bit because square root of 4 is 2. So I could pull a 2 out and get a fully simplified answer of 1/27 times 80 square root of 10 minus 13 square root of 13. Now, that's about as simplified as it gets. I personally don't think that's much prettier than what we had before. So remember, what we had before we simplified was 8/27 times 10 to the 3/2 minus 13/4 to the 3/2. These are the same answer. How you should write your answer really depends on your particular instructor for a course. If you're taking a course with me, I'm fine with this bottom answer. Depending on your homework system or if you have a different instructor, they might want it simplified a bit more. That all just depends on what you've been told. The important part is we knew how to get to this point, and then to simplify it to that is just a bunch of algebra. So that is the length of that particular curve. On that particular problem, we found the arc length by using the formula that we were given, and we ended up having to do a u substitution to finish it up. But it was just a straightforward u substitution. That happens some of the time. Other times we get something a little more complicated. Our next example is a little bit more complicated. We're going to find the length of the curve y equals x to the 2/3 power from x equals 1 to x equals 8. So just a reminder, the arc length formula, which I suggest you write it down every single time until you have it memorized. Integral from a to b, square root 1 plus the derivative of our function squared, dx. So my a is going to be 1, my b is going to be 8. To figure out f prime of x, we need to take the derivative of this x to the 2/3. Using the power rule, that derivative is 2/3 x to the negative 1/3. So let's go ahead and plug what we know into this problem. The arc length is equal to the integral from 1 to 8 of the square root of 1 plus 2/3 x to the negative 1/3 squared with respect to x. And just like the last problem, you should start by squaring that derivative, because that's going to make it a little bit easier to figure out how to do the problem. What we get when we square that derivative, I'm going to have my 1 plus 2/3 squared is 4/9. And then I have x to the negative 1/3 squared. You multiply those exponents to get a negative 2/3 power. And now you're looking at this one, and it doesn't look that much different from what we had before. And you might think, hey, let's just do u substitution, let u equal everything under the root. It worked last time, it should work this time, right? Wrong. If we try to let u equal everything underneath this root, notice what happens when I take my du. I would end up with a negative 8/27 x to the negative 5/3 dx. And if I solve that for dx, I'm going to have x's and u's in my problem at the same time. We can't do that. We don't know how to integrate with x's and u's at the same time. We would need it all turned into u's. So we cannot do u substitution straight away. What I would suggest you do is first rewrite this x to the negative 2/3 down in the denominator. 1 plus 4/9x to the 2/3 dx. Now I'm going to simplify what I have under this root by finding a common denominator. The common denominator would be 9x to the 2/3. So if I get a common denominator, I have a square root of 9x to the 2/3 over 9x to the 2/3 plus 4/9x to the 2/3 dx. And if I add those two fractions together, then I have 9x to the 2/3 plus 4 over 9x to the 2/3. And right now you might be thinking, what in the world are you doing? You're making this integral look worse. And for now, I agree with you. It does look worse. But what we're doing is actually going to make the problem easier to solve. We know that a square root of a fraction is equal to the square root of the top over the square root of the bottom. So I have a square root of 9x to the 2/3 plus 4 over a square root of 9x to the 2/3 dx. Take a look at the denominator. We can simplify that square root. The square root of 9 is 3. Square root of x to the 2/3 is x to the 1/3. So if I simplify by taking the square root of that bottom, we get an integral from 1 to 8 of a square root of 9x to the 2/3 plus 4 over 3x to the 1/3 dx. And yeah, that still looks pretty terrible, but the reason we did this is because now we can use substitution. If I try now to let u equal everything underneath that square root, what would I get for my du? du would be equal to, let's see, 6x to the negative 1/3 dx. That's the same thing as 6 over x to the 1/3 dx, which means my dx is equal to x to the 1/3 over 6 du. Take a look at what would happen if I replace my dx in the problem with x to the 1/3 over 6 du. Then that x to the 1/3 will cancel my x to the 1/3 in that denominator, and we won't have x's anymore. We'll have only u's in the problem. So this substitution is going to work. We still need to change our bounds of integration though. When my x is equal to 1, that means that u is equal to 9 times 1 to the 2/3 plus 4, which is equal to 9 plus 4, which is 13. My lower bound is now 13. When x is equal to 8, my u will be equal to 9 times 8 to the 2/3 plus 4. 8 to the 2/3 is the same thing as 2 squared, which is 4. So I have 9 times 4 is 36, plus 4 is 40. So my bounds are going to be 13 to 40. All right, so now we need to change all of this. I'm going to erase part of this substitution, keep this integral up here so that we can see what's going on. Notice that I'm going to have, let's see, I can erase this stuff here that we got for our work. And I'm going to just rewrite what we needed here. All right. I want to keep this integral up here at the top so you can see for sure how I'm rewriting it using our substitution. I'm replacing my bound of 1 with 13. My bound of 8 is now 40. I had a square root of 9x to the 2/3 plus 4, which is now a square root of u. In the denominator, I had 3x to the 1/3. My dx is x to the 1/3 over 6 du, and you can see my x to the 1/3 are going to cancel out. So when I cancel out those x to the 1/3, I'm going to get an integral from 13 to 40 of a square root of u over 18 du. And this is an integral that we can actually do. So let's go ahead and pull the 1 over 18 to the outside and rewrite our square root of u as u to the 1/2. And now we can do our power rule. So I get 1 over 18, antiderivative of u to the 1/2. We get a u to the 3/2, and then divide by 3/2, which is multiplying by 2/3. And then I'm going to be plugging in a 40 and a 13. So then what do I get there? Well, 1 over 18 times a 2/3 is the same thing as 1 over 27. And I have u to the 3/2, plug in a 40, and plug in a 13. And now we're almost done. Plug in the 40, plug in the 13. And again, depending on your particular class, you might be able to leave your answer right here. I'm okay with your answer right there, but sometimes people want it more simplified. So this is a correct answer. If you were to simplify it anymore, well, 40 to the 3/2, that's the same thing as 40 times the square root of 40. And 13 to the 3/2 is 13 times the square root of 13. And I can simplify that square root of 40 as 2 times the square root of 10. So I get 80 square root of 10 minus 13 square root of 13, and that's probably about as simplified as it can possibly get. So either of those answers are all right. It just depends on how much you need to simplify for your particular course. Again, I personally like it this way because I don't see how this is any more simplified than this. And so I don't usually waste my time simplifying anymore. But you should always do what you've been instructed to do for your particular course or for your particular homework system. All right, so that was an example that was a little bit more complicated. We ended up having a negative exponent when we did that one. When we had a negative exponent under that root, we moved it to the denominator, got a common denominator, and then took the root of the top and the root of the bottom, and we were able to use substitution at that point. So our first example just had straightforward U substitution from the beginning. The second example, we had to first find a common denominator, simplify our root, and then do U substitution. And I have one more example where something else happens. Let's find the arc length of the curve y equals x squared minus 1/8 natural log of x. Between x equals 1 and x equals 3. So reminder again, what is your arc length formula? Integral from a to b, square root, 1 plus your derivative squared dx. So on this particular problem, my a is going to be 1, my b is going to be 3, and I have to find the derivative of this function to plug it into that. So if my function was x squared minus 1/8 natural log of x, well then my derivative is equal to 2x minus 1/8x. Remember, the derivative of the natural log is 1/x. So this guy gets to be plugged in to this arc length formula. My length is the integral from 1 to 3 of the square root of 1 plus 2x minus 1/8x squared dx. This one's a little bit different than what we had before. And what I would do first is go ahead and distribute all of this. Take care of that squaring. Make sure you distribute it completely. So I'm going to have a 1 plus a 4x squared, and then I'm going to have a minus 1/4, another minus 1/4, and a plus 1/64x squared. And now let's simplify what we can underneath that root. We have an integral from 1 to 3 of a square root of, and I'm just going to write it, I'm going to rearrange it a little bit. I'm going to put 4x squared first. My 1 minus a fourth is positive 1/2. And then I have a 1/64x squared. Now, this is something that people tend to struggle with. How in the world are we going to simplify this guy? I look at that and I know I can factor it. I don't know if you guys realize that this is something that is factorable. What I have underneath that square root is actually a perfect square. Take a look at this and see if you agree. I have a 2x plus 1 over 8x squared dx. Do you agree? See if you can figure that out. Let me just check that real quick. If I had 2x plus 1 over 8x times itself, 2x times 2x is 4x squared. 2x times 1 over 8x is 1/4. Again, another 1/4. And then that guy is 1 over 64x squared. The middle 1/4 add to 1/2. So this is perfect squares. And the reason I notice that is, notice that this first guy here is something squared. It's 2x squared. And this guy is 1/8 x squared. And then this 1/2 in the middle just comes about from doing the other distributions. So you just kind of notice that pattern and start recognizing that this can be factored. So if you get something that looks sort of like this, you have a perfect square here in the denominator, and just a number in the middle, try factoring it like this, because that's probably what's going on. Now, why do I care about factoring that? Well, because now I have a square root of something squared. The square root and the squared cancel each other out, and we get an integral from 1 to 3 of 2x plus 1 over 8x dx. This is something that we can now integrate. I'm going to rewrite it just ever so slightly. Notice that this guy, 1 over 8x, is the same thing as 1/8 times 1 over x. Now let's do our antiderivative. Antiderivative of 2x is x squared. Add 1 to the exponent, divide by 2. Then for this guy, I get a 1/8. The antiderivative of 1 over x is natural log absolute value of x. And then I need to plug in a 3 and plug in a 1, and I'm finished. Plug in the 3, and we get 3 squared plus 1/8 natural log of absolute value of 3, but that's just 3. And then I have a minus 1 squared and a minus 1/8 natural log of the absolute value of 1. And then we can simplify it a little bit more. That's 9, 1/8 natural log of 3, minus 1. And then what's natural log of 1? Natural log of 1 is 0, so that last term has disappeared. And now I can just combine my 9 and my minus 1 to get 8 plus 1/8 natural log of 3 as my final answer. So we had 3 examples in this video, and they were all done slightly different to actually get the integral to work out. That, to me, is what makes integration so fun, is you always get to do something different on the problems, and it's fun trying to figure out which way to do it. I understand that's a little more frustrating when you're learning the material and you always want to do something one way. So at least be happy we have a formula to start with, but after the formula, you might have to play around with how to actually calculate the integral. Sometimes you might just do straight up U substitution like the first problem. Sometimes when you have that negative exponent, you might want to get a common denominator, split it as root of the top and root of the bottom, and then do U substitution, like our second example. And then sometimes you get something weird like this last example, where you end up with a perfect square, a number, and another perfect square with the variable in the denominator. And it factors beautifully, canceling out the square root without any substitution at all. So those are at least 3 techniques that you can try on problems, and that covers a lot of the situations that you'll see when you're trying to find the length of a curve. If you have any questions, feel free to drop them down below. Or if you're a current student of mine, you can also ask in email or office hours or in class. And I will see you guys next time.